Which I'm sure you're pleased about. At any rate, Reinhard Werner is going to tell us about, as it says, spectrum and propagation in electric quantum walks.
Okay, so thanks for coming here, everybody. And of course, thanks for the organizer to put together this whole workshop, which is, I find, extremely enjoyable. So what I'm going to tell you about is a very simple model system in which you can study some of the interplay between spectral properties and propagation properties of quantum dynamical system. And so the whole character of the talk is to take this model system and maybe draw some general conclusions about how we should go about that. So one of the basic paradoxes in this model is that you can experimentally see different behavior between rational and irrational values of a certain parameter, which is somehow shouldn't be possible, but in a certain sense it is. And I'll take this apart very, very carefully. Okay, so here's my outline. I will describe the system, of course, and the mathematical and physical background. Actually, there is an experimental group doing exactly these experiments that we are collaborating with. So the few experimental slides, if you want to bear with me. Then I'll explain what the typical observations in the system are. I give you the analysis of the case where this parameter is rational, because there one can make very explicit statements. And then what I consider the main message here is in what we can learn from this rational case when we want to use it to approximate a more general number, right, like an irrational number, and what happens in that case. So actually continued fractions appear there. I will I'll put in a little, mini course on the continued fractions, because I guess it's not typical physicists' education. But they're exactly what is needed here, and in a very nice way. So, and then I'll describe what we can say in terms of that, and draw some general conclusions in the end. Okay, so the system is very simple. It's called a quantum walk. So it's a discrete time quantum system. The Hilbert space is just the discrete, just the integers. That's for the position variable is just integer, so it's living on a lattice. And there is an eternal degree of freedom, which is sort of tensor to it. So the basis states are like that, and particle at x in eternal state. Now there are three operations that play a role. One is so-called spin-dependent transport. So depending on the value of this internal degree of freedom, the things are shifted to the right or to the left. Alpha is plus minus 1, so this is a shift to the right or to the left. The second operation is something that doesn't affect the x variable at all. It's just a unitary reshuffling of this internal degree of freedom. And so these two together, that's a very well-studied subject. And the not so well-studied addition that we are considering here is an additional phase that is put onto the system that depends linearly on x, on the space. And the critical parameter that will be the most interesting parameter in this whole thing is the value of phi here. I put a 2 pi in so that it really is the rationality or irrationality of this electric field phi with respect to the lattice constant. And so actually I'm not going to explain in much detail why I call that electric, but the general approach here would be to say that if you wanted a quantum walk in a magnetic system is one in which the translations are made to commute only up to a phase. So you have a new kind of translation group called magnetic translations, and they commute, but only up to a phase, which can be sort of compensated by a gauge transformation. And an electric field would be the same, where the time evolution operator, which is this W, commutes with only up to a phase. So this is the kind of phase that goes in here. I don't want to go into this general philosophy too much. But the overall time step is just a composition of these three things every time. Okay, so let us first put this field equal to 0. And so if you have the non-zero field, then of course this whole thing is not translation invariant, right? Because there's an explicit x dependence here. But if we put the phi equal to 0, let me just remind you how the analysis works in that case. This is a translation invariant case. And of course, what you do is you Fourier transform. Jointly diagonalize everything with the translations, because everything commutes with the translation. So this gives you a decomposition of irreducible representations of the lattice translations, which is called the Briand zone by physicists. And so you make this kind of Fourier transform, and the walk operator that commutes with the translations then becomes multiplication with a p-dependent unitary matrix. And this unitary matrix will be a polynomial in the e to the i's, which you get, but just you can just read off this matrix from the representation of coin. I mean, how the coin looks, you can just write down the W. So it becomes a multiplication operator with respect to the p's, but some non-trivial unitary rotation that depends on the p. Okay, so for each p then you can diagonalize, and you find, so this p-axis here actually should be read with periodic boundary condition. This is the Briand zone, or the dual group, if you want. So this is like a circle down here. And also the phases, of course, the eigenvalues of a unitary operator are phases. So there's also a periodic closure here. So the whole thing lives on a torus. So what you're seeing here is a curve that sort of winds around the torus. Could be several, but certainly what goes out here has to come back here, and what goes out there has to come back there, and so on. It should be okay, that maybe from my angle it doesn't look quite convincing, but I'm sure it's correct because, of course, I draw that in Mathematica. Okay, so one basic fact here is that the spectrum of such a system is absolutely continuous. If you look at the spectrum of this walk operator, it is a multiplication operator. So you can think of this as turning everything into multiplication operators after you also diagonalize for every value of p. And what you multiply with are these values, and they are sort of a continuum. And apart from a functional determinant that might diverge in some points, but otherwise it's a multiplication operator, and the spectrum measure is absolutely continuous with respect to the Lebesgue measure. Should I? Yeah.
Well, there are no degeneracies.
It can actually happen that there would be a flat band, even in this situation that I described with a polynomial W. What other degeneracies are, I think? Oh, there could be several sitting on the same. Several of these curves could be sitting on top of each other. So this is counting multiplicities, of course. Yeah.
What does absolutely continuous mean?
Okay, so if you look at the spectrum, you have the spectral resolution of your operator. That is, there is a projection valued measure for the probability to find its value in a certain interval. And now if you take the expectation value of that, you get a scalar measure. And absolutely continuous just means that it has a density relative to the Lebesgue measure. So this will come up later. I mean, this is why I'm also answering this very explicitly. So there are actually three types of measures that occur in the spectral theory of this kind, and they all appear in this talk. One is pure point, that is all eigenvalues. These eigenvalues, because this is an infinite dimensional system, the eigenvalues could actually be dense in an interval or on the whole circle. Then you have this absolutely continuous part, and you have a singular continuous part, which is sort of the rest. So most physicists, I guess, don't like to see any singular continuous spectrum, because this is considered kind of exotic, but here actually it happens quite naturally. So every measure can be decomposed into three parts with these properties, and that is also something that will be dynamically relevant. So here it's all absolutely continuous, and we can also say something about the propagation. So spectrum and propagation are the two themes in this talk. So propagation here is that if you look at the operator of position divided at time t divided by t, so you can also write it like that, this converges. This converges to an operator which we call the velocity operator, or rather the group velocity operator. And the way to compute it is that if this is your spectral resolution of the walk operator with these p-dependent eigenvalues, Then you differentiate these functions, and then you get something like a velocity. And this is you don't change the eigenfunctions, or the eigenprojections, but you take these derivatives instead for the eigenvalues. This gives a group velocity operator. Actually, at this point, you have to discuss carefully what happens at crossing points and so on, but I'm just sweeping that under the rug. So what does that mean? That is, if you want to look at where the particles are after a long time, then they will basically be at t times v. So it's a distribution that spreads ballistically, as they say, so proportional to time. And the profile will be given just by the expectation value of this v operator, by the distribution of this v quantity. Right? So let me show this in more concretely. So this is the Hadamard walk, particular choice of coin. This is just the probability density. Sorry, this is a discrete probability, just the values of the probability plotted over time. And here it's the same plot, but scaled with 1 over t. So it's x over t here. And you can see that this sort of converges to the blue curve, which is the probability distribution that you get directly from the v operator. Right? So you get the asymptotic form of this of the probability distribution. So this just spreads apart. So the spreading of the wave packet, but here with the scaling, you see that it does converge to something in the weak measure sense. Right? So okay, so that's the ballistic scaling. Now let me just say a few words about the experiment. This is our collaboration with the people in Bonn. Dieter Mescher is there on the left, and they have a very nice system in which, first of all, you create an optical lattice. You do that by counter-propagating lasers. So this is a standing wave field, and in the maxima of this field, you can trap atoms. They are cesium atoms, and you can cool them nicely to the ground state. And your workhorse here is the qubit, actually, or the internal degree of freedom, two particular hyperfine levels that they single out for various reasons. One of them, of course, being that you have a nice radio frequency driving mechanism here, so you need your microwave, right? So you, by microwave radiation, you can control these things, make the coin operation, for example. And these levels are sensitive to opposite polarizations of the light field. So you have a spin-dependent transform, which here you need an electro-optical modulator, and by that you can you can shift the two polarizations of your standing light field with respect to each other by changing a phase there. And this will take particles in one state, move particles in one state, and the others in the opposite direction. Okay, so you can do this Galton board type evolution. So the time scale here is 100 milliseconds. This is basically an optical wavelength here. And well, you can just then, these are the pulses, the control sequences, and you get histograms like that. They have these two peaks that you just saw, and well, quite different from a classical random walk. Actually, there will always be some decoherence in the system, and that eventually takes over. You do get something like that. But as long as you can run it coherently, then you see these double peaks, and this follows very nicely the theoretical prediction. So actually, in order to check for the coherence, you can run the same steps backwards, and then the criterion would be that they have to end up at the same point. So you invert your Galton board, which you can't do with a real one, right? So you have a similar Galton board, will always keep spreading, but here you actually come back to the same point, well, to within experimental imperfections. These are actually quite old data. By now, they are much better. But that's the basic picture that you always get. Now, the walk with non-zero electric field can be done in the system by shifting the whole lattice at with an acceleration. And the acceleration basically gives you the value of the field. So one good test of this is that you can compute how this phi is translated into an acceleration. So if you accelerate, and they can accelerate so much they get the whole phase, like the 2 pi I phi will be 1, right? So you can go back to the same situation, and then you should see no effect of that phase, and that's indeed the case. So they can really adjust any kind of electric field. And then what they do see is a strong dependence on the value of this field. So you try a simple rational value, and you can try something very irrational, and you see a difference. So let me run this. So the first panel up here, maybe look here. This is what I just showed you. So this is just a free walk, fields is 0. Here we take a simple rational like 1/5, and you see basically the same picture. It's a bit rougher, and actually the propagation is a bit slower if you look at the scale, but still it's basically the same thing. Do I have to restart this? So let's look at another rational, 51/256. It also does more or less this game, but it comes back to the origin again. Zack. This was one revival. Here's another revival. So it really comes back to what it was initially, which is kind of strange. And so this is just another rational, and if you take a very irrational number, like the golden ratio, then maybe this time just look at this one. It wobbles a little bit, but basically remains stationary. So you do see some, these are computed, but the experimental curves look kind of similar. Okay, so this is again, the experimental curves would be just measurements of this per time. I mean, you have to decide beforehand how many steps you want to do. Of course, you can't look on the way because that would totally destroy the system. But then you would then say go for like 17 steps, make your experiment, look at the histogram. And I was just sort of, to animate that, I found it more convenient to do it numerically. Right? So
how accurately can they dial in phi?
Pretty well. But so they might just be able to see the difference between these two, but maybe not quite. No, actually, they are very close. So that's maybe a bad example. Of course, that's a very finite precision. Right? And this is, of course, the topic of my talk. Okay, so again, the rational cases, what I plotted here is the variance of the position distribution. Now, I told you have ballistic spreading, so this should be going up linearly. And so this is actually what you see. And then there is a return probability. Well, since this thing spreads out, the return probability, that is the probability to be back at the origin, goes to 0. Right? So this has a Bessel function envelope, but it goes nicely to 0. For this other fraction here, of course, this is very close to 1/5, as you can see. And it's very close to 1/5 in a special way that we'll understand later. But therefore, it's clear that the initial part of this, so the scale is a bit different here, right? But this black rectangle is equal to that one. So if you look at the initial part of this evolution, it actually falls exactly on the other one. Right? It has to, because all the expectation values that we compute, of course, depend continuously on this phi. Right? Now, only when time goes on, this becomes more and more sensitive. And we'll discuss that. So the initial part of this is the same, but then you will see it will come back to very closely to the same point. This was the revivals that I called out revivals. And of course, then after again the same number of steps, it's again almost the same, right? Because you reproduce the initial state here very closely, actually exponentially in the denominator, but I'll come to that. So you have a very sharp revival here, and actually if we can compute this, the theory I'll show you later will completely describe that. So this revival is very sharp, and this pattern will repeat about 10 to the 19 times before it starts going ballistic, because in the end, this is just another rational. You can regroup your system. The basic analysis for translation invariant walks holds on a slightly larger scale, well, factor 256, but it's basically the same thing. So this will go ballistic eventually. So it will do this, and this curve will also decay, but after quite a while, like 10 to the 19 repetitions. If you take more complicated rationals here, that is larger denominators, this will be even larger. So the irrational case would do something like this. The same diagrams for that would look like this. So the variance basically oscillates a little bit, but in a somewhat irregular way. And the return probability always remains high. It never goes to zero or anything. You can always, whatever the time is that you let it run, there would be a fairly high probability to find it back in the same state. So this is a picture of something staying put in one place. Okay, so so the analysis can be done, so in the rational case, the analysis can be reduced to the translation invariant, basically. There are two possibilities to do that. One is to do a grouping in space. That is, you take m sites together, where m is the denominator of that field. Of course, if I take n and m coprime. Right? So, and then you group m sites and call that one supersite, which has just a few more internal degrees of freedom. And then it's clear from that that you just have a translation invariant walk with ballistic transport, eventually at least. But you can also group in time, which is something that I'll show you later. Then you have a translation, so after m steps, actually the phases cancel, and you get something which is again translation invariant. So this is easier to analyze because this has coin dimension 2, and we can do that more explicitly. The surprising fact that you just saw, or at least you saw some of it, is that after a number of steps for which when m is odd, the denominator here is odd, after exactly m steps, you see a revival, which is that the whole walk operator is close to the operator -1. Right? So you should read that as minus 1. This -1 is just a phase. So up to a phase, this norm will be exponentially small in m. This a is the parameter in the coin here. It's typically, for the Hadamard walk, it's 1 over square root of 2, from which you get this kind of estimate that it takes 10 to the 19 repetitions, because that's like 1 over square root of 2 to the power 256. That was the denominator in that case. In the even case, it's very similar, only that you need to make twice as many steps. So this revival that's very paradoxical. Right? So if the denominator is large, this revival happens after a long time, basically the time of the denominator. And then it will be, the longer this takes, the sharper it's going to be. And not just a little bit, but exponentially sharp. Okay, so how do we get this? Let me prove it, or at least sketch how it goes. Right? So, so these are in momentum representation, these are the shift that only multiplies with e to the 2 pi I p, basically. Right? And alpha is just a plus minus 1. Then there's a coin, nothing wrong, there's nothing special about that. And the field is multiplication by a linearly growing phase, which just means a shift in the Fourier transform. So you're shifting your basis vectors. Right? Now, if you multiply m, so m is the denominator, and if you multiply m of them, then this effect here means that if you apply this on a wave function, you first apply the walk operator. But then you have also the shift, so in the next step you apply the walk operator at the point p plus phi, and so on. But changing p by phi means that you have a different shift operator that just is the e to the 2 pi I plus minus 1 times phi. So this is a fixed operator times a Pauli 3 matrix acting in this matrix space. So you can replace that by the original walk and a matrix like this. Right? And this has progressive powers. So it grows because you go from phi to 2 phi and so on until you've actually made the complete round. So all the powers, the different distinct powers of this operator R appear here sandwiched in between the free walk. So the basic thing is application of the field means a shift by now a rational amount. Right? And after a certain number of steps, you get back home. So this is the kind of expression that you have to evaluate, or we want to evaluate that. We take this walk operator and take its trace. So this is the x will be just a free walk operator, or something like that. and it's sort of interlaced with power, all the distinct powers of this operator R. And our claim is that we can compute this trace very compactly. Namely, it consists of just two terms, which are the 1 matrix element to the power m plus the 2 matrix element to the power m. So this trace, of course, has, if you write it out, the product and the trace and so on, you have an exponential number of terms, but in the end you just have 2. Okay, so how does that work? Here's this expression again. Well, if you think about evaluating such a trace, and we do this in the computational basics, where this R is diagonal, right? Then these R's are just multiplication by certain factors, and if you go through this trace, you have one index that you start with, let's say 1, and then you have maybe the x1, 2 element, so they have a 2 here and so on. So you can follow a sequence of indices that do all the operator multiplications and the final trace. So you have a path in this diagram of length n between index 1 and index 2. You have to get back home because it's a trace. Right? So this is a closed loop in this on this graph. Now, this means this is clear. So every time you go this way, you have an x11 factor. If you go from there to there, you have a factor x21. Here you have a factor x12, and so on. Right? So it's clear from this that x12 and x21, which are the flips between the two, have to appear in the same power. So the whole thing, which is clearly a polynomial in all the matrix elements of x, will have the same power for x12 and x21. There is another symmetry which is very important. That is, when you multiply x by r, then you basically just cyclically rotating this trace. So this substitution doesn't change the trace, which means, but effectively, this just puts this factor on the trace and on these elements. So, you also see that this overall, any monomial that you have in the expanded expression here will be multiplied by a power of phi r minus t. Right? So, this puts a constraint on the monomials that can actually still appear. So the monomial that can contribute must have r equal to t mod m. It could be like 0 and m. That's also one possibility. Or r plus 2s plus t. That is the overall, and that's the other constraint. The overall degree, this is a homogeneous polynomial in x. So the overall degree has to be m. That's this equation. So I think I said somewhere I wanted to look only at the odd case, right? Because the even is kind of analogous, but the odd is easier. So here are then the conditions. How could this happen? Well, you could satisfy this by having s equal to 0, and then r and t are either equal, or one of them is m and the other is 0. So this is one case, and these are just opposite to each other. So these are the two cases. But when r is equal to t, then you look at this expression, then you have r is equal to t, so you have an even number m, which contradicts the oddity of m. So that is, these odd terms in the odd case, everything is ruled out except all the r's are equal to all the indices are 1, or all the indices are 2, and those are just the two terms that are standing here. Right? Okay, so as I said, the even case is a bit more complicated, but not much. So, so the revival theorem then goes like this. I mean, this is the mth power of the walk. We look at the trace, and the trace is, we could just put in the matrices, we know them, so we have an mth power. There was also an imaginary thing, and you have two terms which add to a 2 cosine term. Right? So, so this trace is exponentially close to 0, because a is a number less than 1. And then if you look at where the spectrum could be, so here's a picture of where the spectrum of such an operator could be. Maybe somewhere on the unit circle, but if the trace is 0, the sum of the two, it's just the real part basically. If that is 0, you can only have these 2 points, or we have a small strip around this axis where the eigenvalues could be, here and there. But this means that the second power of this operator will have all the eigenvalues sitting here. If you just multiply these two phases, either way, you end up at -1. So you see that, so this is the revival statement that I made. So all the eigenvalues are close to -1, which means the operator is close to -1 times the identity. And this is true for all p. So it's actually uniformly and sort of as an operator on the whole Hilbert space, it's still close to -1. Okay, so this explains this revival structure. It's this trace formula that gives you that. Okay, so now about as I said, the stuff that I really wanted to tell you about is the question, what do I learn from that about the general case? So now we've done the rational case, we understand these revivals, but what if I just put in any old phi, right? Typically, of course, irrational. So, first of all, this is a trivial observation, but important, of course. For finite experiments, this distinction is irrelevant. So whenever your total duration of your experiment is finite, you could never see the distinction between phi rational and irrational, simply because it's a continuous function and so on. So all statements about dynamical properties for finite times that are valid for some rational value will also be true in the vicinity of this value. So if I have a good rational approximation of my number, then I can use what I know about the exact dynamics with this rational to learn something about the irrational case. Right? And the question is, how well does this work? Well, and of course, even when both fields are rational, the approximation between the two will be of some interest. This is like the initial phase of the evolution that I showed you. You can still make some conclusions about the structure of the revivals in the general case. But let me follow this approximation idea. So how good is this approximation? That is, how continuous is this whole thing with respect to phi? Now, the only place where the field enters is this multiplication operator. So it's clear that in terms of norms, you can just estimate these. Phases. Wait a minute. What am I saying here? Yes. So let's look at this multiplication operator. It's a multiplication operator that depends on x, right? So when phi is different from phi prime, then somewhere in this system, that is for large x, you will see an appreciable difference. So these operators are actually always have norm distance 2. So if you look at them if you look at the whole thing in the sense of norm approximation, that is a uniform approximation across the whole system, then they are always sort of as far apart as unitary operators ever can be, because somewhere there will be a large difference. Right? Now, therefore, we have to do something different. So we have to look at the case where we apply this on a wave function of which we know where it is. It's supported, let's say, on sites closer to the origin than L. Right? So fix some L, and then you apply it. And then, well, the maximum difference is, so the difference between these operators will be just the maximum of these phase differences over of the interval that you're looking at. Right? So if this L is infinite, this is 2. Right? You can always find one that cases where this is far apart. But if L is finite and phi and phi prime are close enough, then you just have to take the maximum here. And this is very easy to compute. This is basically the length here times the difference of these slopes, right, of phi and phi prime. Okay, so this is for one step. For one step, you have continuity in this sense. And you see that the evolution will be the same, provided you start from a kind of localized wave packet. Now, you can iterate this argument and make more steps, and this is this one. So you take this estimate and you iterate it. But now, every time you make a step, you know that this shift operator can lead you further away from the origin. So actually, L increases by 1 in every step when you make this estimate. Therefore, if you add up these constants, these increasing L's from L0, let's say, to L plus T, then you get this quadratic expression. Right? So the the error estimate that you get is quadratic in t. Okay, so this is one of the key messages here. So how well do I have to know the difference between phi in order to make a reasonable prediction on some time scale? Well, for example, I would want to predict the revival at time t equals m, and the field, so there's a field close to this rational value where I know there is a revival. So how relevant is that piece of information when I take another field closer? So phi is an irrational field, phi prime is a rational one nearby, and I know this has a revival at point n after m steps. So what do I learn about w phi? Does it also have a revival after so many steps? Well, in order to make that conclusion, I need actually that m squared, which was now the number of time steps that we make, m squared times the difference is small. So you have to, and this you want this small, so you need an approximation of this sort. So you take your irrational field is supposed to be approximated by this rational phi prime to within a quantity like this, which is quadratic in the denominator. And this quadratic nature comes from this fact that you're really looking at a linearly progressing slope and the system is expanding. Right? So we need a better rational approximation than you can get for free. Right? So if you want to make a rational approximation with a given denominator m, of course you multiply your number by m, you take the integer part, and you have an approximation which is good in 1 over m, basically. Right? So that's what you can do for an arbitrary denominator. And there are some special denominators which allow this kind of approximation quality. And what we need now is the theory for approximations of rationals that are better in exactly this sense. Okay? And this is just before I go on to that, this kind of linear expansion is very typical for many quantum dynamical systems. And whenever you have parameters that sort of enter linearly, like external fields, like electric or magnetic fields, then you will have this kind of quality. So you need to know your parameter to within this sort of approximation. Okay, so we need to invent a theory of such rational approximations. Well, we don't need to invent it because it exists. Right? So that is exactly the theory of continued fractions. Now, this will be my mini tutorial on continued fractions, and I guess in a place like this, it's a bit absurd to do that, but anyway, we are mostly physicists, so let me do it anyway. So I don't think this is in most, I mean, well, I won't ask you for show hands, but I guess if you're brought up as a physicist, you probably won't have seen this in any detail. But so the basic idea is that you have this typographical nightmare. Right? C naughts are some numbers. There will be integers in this case, and you just keep on adding such fractions, and you try to represent a number x by it. Right? And of course, you have rational approximants. When I take these 3 dots here and just replace them by a 0, right? I don't continue the fraction. I terminate it somewhere by a 0 in this place, and then of course multiplying it all back together gives you some rational number. Right? So these successive rational numbers that are associated to x are called the convergence of x. And so there is a theory that, let's say, yeah?
Well, so this is just a beginner question, but it looks like if you calculated this through to the C5 or something like that and cut it off, to get like a next additive term or multiplicative term would be difficult, right? This is, at least according to this formula, it would be hard to like.
So the whole thing is so actually the place where you can find all this is, for example, Hardy and Wright Theory of Numbers, a beautiful book that lays this out in all detail. And indeed, for number theory, it's important to do such rational approximations, and that's exactly what we want here. We want good rational approximations. That's the sole aim. So anyway, I can go from this sequence to the number x and back in the following way. So if I have if I have the number and I want to get to the sequence, here's the algorithm. I start with this, I go through certain numbers r. I start with x. I take the integer part of x. That's my first approximation. It gives my first term, my first c term. Then I take the difference, the fractional part in this decomposition, which is that, and I invert it. I take 1 over the fractional part. Now this will be my next r, and then I go on and take the integer part of that, take the difference, invert it, take integer part, and so on. So this is the algorithm. So let me just run that on the number pi. Right? So pi r naught will be the integer part of pi is 3. The fractional part is this guy. So if I invert that, I get 7. So C1 is going to be 7, and so on. So here's actually the continued fraction expansion. Mathematica gives you that in no time to thousands of places. Right? Now the opposite, going from the sequence to the number, is actually a simple linear system. A linear difference equation where here is the system, and the coefficients are just these c's. And so p and q are actually just the denominators. So the approximants will be just pn over qn. I didn't write that here, but here it's written. Right? So let's do that for pi. Here's the sequence that we computed before, or Mathematica computed for us. Let's look at this entry. So 22 actually arises by 7 times 3 plus 1, right? And so on. So, and the approximation here is 1 part in 10 to the 4, which is way better than 1/7. Right? So if you try to approximate pi with a denominator 1/8, it will be much worse than this. So it's these special denominators that appear in the continued fraction expansion that allow you to get these extraordinarily good approximation. Like here, 1 part in 10,000 instead of 1 part in 7. Right? Here's a really good one, because actually this is related to the fact that this is so large. So the basic, if you look at the remainder term here, first of all, you can show that in this iteration, Pn and Qn are always co-prime. So this is because of this. So there's a determinant argument here that tells you that this is that these two successive rational approximations are also always very close. And from that you directly get the estimate that the basic estimate is this, right? So the basic error estimate is that the nth convergent of a continued fraction is close to the number, quadratically good in the denominator, and actually the constant here is the next continued fraction number. So this is all from Hardy and Wright. But but as I said, this is the theory I would have had to invent if it hadn't been invented already, because it gives you these quadratically good approximations. Okay, so the convergence is therefore worst when these terms are all small. So the smallest they can be is 1, and the continued fraction that goes 1, 1, 1, 1, 1 is the golden ratio. So it converges to this guy. Actually, the continued fraction expansion is periodic if and only if you have a quadratic root of an integer in your number somewhere. And so the convergence are the successive ratios of Fibonacci numbers. Right? So in that case, because this iteration that I showed, oops, where is it? Here. Here's the iteration. When the c's are all the same, this is just the Fibonacci iteration. Right? Your nth term is the sum of the two previous ones. Right? Okay, so this is my crash course on continued fractions. Anything else to say about continued fractions? It's a cool theory. I don't know. Okay. So now let us look at the continued fraction expansion of probably phi, right? Then we can actually make this revival prediction. So there will be appropriate phases, so that after 2 times the continued fraction denominator, we are basically back home, and the error term, there is an exponentially small error term that I sweep under this carpet here, But basically, the quality of the approximation comes from this 1 over next continued fraction term. So these CKs of the continued fraction directly show you how good the revival is promised to be by this theorem. Right? And there's a distinction between the even and the odd case here. But basically, it's the same revival statement I had in the rational case, but now changed according to the quality of my rational approximation. Okay, so large Cn. So whenever this continued fraction term is large, you get a very sharp revival. And of course, this if you take a typical phi, this is also in Hardy and Wright, you find that the bounded continued fraction expansions are measure 0. Particularly periodic ones would be bounded, right? But actually there are lots of estimates telling you what is the Hausdorff dimension of the set of numbers that have a certain growth behavior and so on. This is very, very well studied. Right? So, but certainly, in a generic case, that is if you take Lebesgue random value of phi, almost surely this will be an unbounded sequence. That is, you will have arbitrarily good revivals after some time. Right? Okay, so now just a few remarks on spectrum and propagation. I mentioned to Charlie's question, I mentioned these 3 spectral components: the pure point, the absolutely continuous, and the singular continuous. And so when phi is rational, you have only the singular, the absolutely continuous, no point spectrum, no singular continuous. That is, for example, you don't have any eigenvalues. And so in the rational case, ij is one of these 3 values here, right? So every spectral component is actually closed. That's always the case. And you also know that multiplying the spectrum by a phase is like multiplying the operator by a phase. That is, a multiple of this is equivalent to a spatial shift. So actually, the spectral components will be invariant under these shifts, and because they are closed sets, and the shift goes everywhere in the rational case, they will just be the whole circle. So it's you never have to compute the particular position of the spectrum. So if you have one eigenvalue, you have a dense set, and if there's any singular continuous spectrum anywhere, it's the whole circle, and if it's any absolutely continuous spectrum, it's also the whole circle. No, sorry, just yeah. In the irrational case, where you have this irrational rotation invariance of the spectrum. So there are many statements that connect spectrum to propagation. For example, in the pure point case, if you have just an expansion into eigenfunctions, think of the wave function expanded into eigenfunctions. Basically, each of these terms oscillates with some frequencies, but they never go far away. They always come back home. Right? And so you can fix a finite dimensional space, or whatever your finite dimensional space that you fix, containing the initial state, you won't leave it up to small probabilities. The absolutely continuous is the opposite. So if you have if you're an absolutely continuous spectrum, any finite dimensional subspace will be left forever. And singular yes, actually the continuous spectrum altogether means that on average you leave every finite dimensional subspace, but there could be sort of reversions, revivals. And okay, so this is another topic, monitored quantum walks. There you can actually make a distinction that just picks out the absolutely continuous component. But you have some relationships between spectral and propagation properties, and so let me first show you how you can now make a field that will belong to the singular continuous spectrum. So which is sort of the most exotic kind of spectrum. I guess if you're a physicist, you may not even have heard about it. So the idea is that the singular continuous spectrum happens when you have very good rational approximations. It's not irrational, but you have a very good approximation by a sequence of rationals that is a rapidly growing sequence of continued fraction terms. Right? And if they can grow sufficiently fast, I'm going to show, then the spectrum will be continuous, singular continuous. So suppose that we have constructed our field, or rather the continued fraction expansion of the field to some point. Then we know there's going to be a revival. Right? And now the first thing that we want is that this revival is very sharp, and that means that the next continued fraction expansion is chosen particularly, sufficiently large. It's always in the direction of sufficiently large. So this is something that we can attain by doing that. Now then, this evolution that belongs to that particular rational will go on and on. It has exponentially sharp revivals, right? So it will repeat itself very often, very, very, very often. But nevertheless, eventually it will go ballistic. And because this is absolutely continuous spectrum, it will leave any finite region. And forever, right? So we just have to make the approximation between the irrational, the irrational that we are constructing, and this phi prime so good by choosing ck large that we will also see this ballistic excursion. And we can make this excursion as large as we want. So Rn is some sequence of growing numbers, and we can, since we can make that as large as we want, we have a large excursion. Now we go back to the other step. So this fixes the ck. Right? So then we fix the ck plus 1 to make an even sharper revival and an even longer excursion. So if you put these two together, it will contradict the pure point spectrum, because you're not staying in any finite dimensional subspace because of these large recursions, and it contradicts the singular continuous, the absolutely continuous spectrum, because you're always coming back. You would have to leave every subspace, so the spectrum can only be singular continuous. That's basically the argument, and you get this hierarchical movement, right? So extremely long time scales piled on top of each other, and at every scale, everything that has been happening on the previous scales will be repeated almost infinitely often before it again goes ballistic. So, but anyway, for sufficiently fast growing ck, you get singular continuous spectrum. I should now if you take, okay, let me just try to be quick about that. If you take just any old field, sort of take a random number from your random number generator for the field, what happens? Right? So one thing is you can let's say, or the golden ratio or something like that, something that you know is nicely irrational. Then you can try to build eigenfunctions by putting that on a finite system. This means that you have some perturbation at the point where you cut, right? But anyway, you can diagonalize that. You find eigenfunctions, and you pick the eigenfunctions which has the smallest expectation of x squared, so it's most concentrated on the origin. You can do that for various sizes of the ring, and you will see that typically this converges when you make your boundary condition, your ring larger, and look at larger and larger subsystems, and this is good. This is a good candidate for the eigenfunction. Actually, if you have one eigenfunction, it will be, you know that by irrational rotation you get a dense set. So this is what you get when you put in phi for the golden ratio. This is psi squared plotted for the eigenfunction that you find numerically. And that's certainly one way of doing it. And as I said, you can get them all by shifting and maybe putting staggered signs like that. But you don't really get a proof in this way that this is an eigenfunction. So if this were an exact eigenfunction, you would have complete localization with exponentially localized eigenfunctions. Very nice. That's called Anderson localization. You can get even better eigenfunctions by doing the iteration that if you can write your eigenvalue equation as an iteration in x. This is called the transfer operator method. You also do this in the continuous case. It's very well known from physics courses, I guess. And if you iterate that, you will actually find, so this is the iteration on 2 by 2 matrices, which will have one expanding direction and a contracting direction. Actually, the expansion factor we know, it's called the so-called Lyapunov exponent, which can be computed in this case. So, so you have an expanding direction, and that is after a short while, if you start with a random initial state, you will go off in a certain direction. Now, these transfer operators, when you choose your field in a clever way, will actually be also contracting on the other side. So there's a symmetry here when you choose the eigenvalue just right. So actually we did this first computation that I mentioned, looked at the eigenvalue that you find for the most concentrated eigenfunction, made a continued fraction expansion of this guy and found that it's periodic. So you can, and that it's actually half of the golden ratio that way. Right? So of course you only see the initial segment, but that's also a cool trick to use the continued fraction expansion to identify something that that could be like an exact square root of something. Okay, so then with this method you actually get exact eigenfunctions. This is what I showed before. But then like this is like length is 6,000, and over that many steps you get a clean exponential decay. And this is like 2,000. This is a decadic log, base 10 log. So you get, to some fantastic accuracy, you get exponential decay over a very long step. Still, it doesn't prove localization, because even though you have diagonalized your operator to some absolutely absurd numeric precision, right? This doesn't amount to a proof of localization. We actually are now onto it, and we have a way of doing it, but that's not completely finished, so I shouldn't make too fat claims. So this is my summary for the different types of propagation. When the field is rational, you have absolutely continuous. Nearly rational gives a singular continuous, that is fast growing C. And the typical case will give you pure point spectrum and Anderson localization. So I think I've used up my time. I wanted to make some general remarks here, but maybe I can just briefly indicate what I mean. So we have here if you look at let's say somebody writes down a Hamiltonian, then a mathematician sees the question to compute the spectrum, or this guy, right? So what you would like to compute the spectrum of such an operator, which at the same time has an intimate relation with the infinite time behavior of the system. The moral of this kind of model, to me at least, is that this is somehow the wrong question, because you're really looking at the infinite time behavior. So on very long time scales, you can make predictions in this case, of course, independent of whether this phi is rational or irrational. What you have to know is a continued fraction expansion. So an initial segment of the continued fraction expansion here gives you predictive power over finite timescales, and this is something that you want quite generally. So we should maybe be not too concerned with the precise nature of the spectrum, but with the question of what kind of predictions can we make on a finite timescale. So one example let me just give this one example where similar things like that, they happen all the time, right? So for example, look at the perturbation theory of the Stark effect. You put on an electric field, and then your levels of the hydrogen atom move a little bit. Right? That's a quantum mechanics 101 exercise. What they don't tell you when they put this exercise usually is that by turning on this electric field, the operator loses all the eigenvalues. It becomes completely, absolutely continuous spectrum. And physically, this is the reason is that the Coulomb barrier becomes unstable. The potential goes to minus infinity. So it can tunnel through that. But this happens on absurdly long time scales. So the physically, this perturbation theory computation is very good. Actually, it's very useful experimentally in comparison to experiment. But mathematically, it's absurd because there isn't even an eigenvalue. How can you say that you can that you can approximate an analytic function of the perturbation parameter of something that doesn't exist beyond the point field equal to 0. Right? So we have many situations like that, where something, where this idealization that is very convenient mathematically to talk about the infinite time behavior, rather about that on time scales of the length of the universe or some other concrete time scale like that. So this is mathematically convenient, but also a bit lazy. So there is a challenge here to try to learn more about such systems, not by going all the way to infinity, not by precise spectral characterization, which you can do in this case, but which is nevertheless somehow irrelevant. So what one should try to do is get predictive power on a targeted time scale, maybe something like the age of the universe or so. Okay, so with that I will conclude. Thank you.
Are there any questions?
Oops, yeah.
I have a question. You mentioned localization, which for me, Anderson localization is about random things.
Yes, so
Statement of this disordered system. There doesn't seem to be any randomness here.
so this is not disordered, right? So we have a very highly, this is almost periodic, and there are many analogies between cases where actually, so this is a subject onto itself. That so for some questions, almost periodic, or maybe we have even more periods, and it is just one period here, and so it's called quasi-periodic. And random have similarities, but actually you have very long-range order here. So you shouldn't expect too much equivalence between these, but here actually we do conjecture that is complete. That is, Anderson localization for us means pure point spectrum with exponentially localized eigenfunctions, and I think we can establish that.
Yeah, are there any other questions? In which case, can we thank Reinhard?
Okay, thank you.